Thank you for joining GE's webinar, Building a Successful Transformer Life Management Strategy. At this time, I'm proud to introduce Alfonso Ambrosone and Donald Skelly, our technical product subject matter experts from GE's Monitoring and Diagnostics business, who will be hosting today's webinar. Alfonso?
Thank you, Tracy. Okay, so let's start by having a quick look at transformers. In essence, a transformer is a simple device that is designed to either step up or step down voltage. And the total apparent power of the secondary output is proportional to that of the primary output. However, in real life, a power transformer is a more complicated machine. We can break down the transformer into four major components, plus the control cabinet. So looking at the four major components, we have the main tank, which houses the core, the coils, and the insulating oil, the bushings, which allow the electrical connections from the transformer to the grid, the online tap changer, which regulates the output voltage, and the cooling system, which renders the transformer as efficient as possible. The control cabinet houses all the interconnections between the various controls of the transformer. When we take a closer look at these four major components, all four of these components are subjected to stress during transformer operation, and therefore they are at risk of potentially failing. The failures are not distributed evenly amongst the components, as elements of each component behave differently when stressed, and some of the elements are stretched much more than others. There are also a good amount of failures that are attributed to others. These are what we call non-detectable failures caused by either lightning strikes, severe short circuits, or operational error.
Hi, so Tracy introduced me a few moments ago, but to remind you, my name is Donald Skelly. Now we will take a look at a life curve used to illustrate the failure rate of equipment. So a transformer, in common with a lot of industrial or even consumer products, tends towards a bathtub failure curve. By the way, the name bathtub curve is derived from the cross-sectional shape that you see in this illustration. For typical power transformer populations, the failure rate is high in the first few years as design faults, build errors, or transportation damage to the core, coils, or connectors results in failures soon after the transformer is taken into service. This failure rate then decreases rapidly as defective units are identified and repaired or replaced. In the midlife of any transformer population, the failure rate is low and relatively constant. In the late life, and for transformers this can be considered as 30 plus years of age, the failure rate increases as age and wear and tear take their toll on the product. At some point in the age progression, the rate of failure of a population will exceed an acceptable level, and replacement of all transformers reaching that age may be used as a means to prevent failure. The curve shown here relates to a typical transformer population, and it's well publicized. Individual utilities may have a slightly different shape within their population, but the general shape will be the same. As we will see in later slides, it is shown that monitoring can be used to change the profile of this curve and to reduce all failure rates through condition-based maintenance. So now let's look at transformer monitoring. So today we will discuss transformer monitoring, and this discussion begins with the question, why should a utility or industrial consumer monitor their transformers? Firstly, it is accepted that transformers are a key component of the electrical power grid, whether at generation, transmission, distribution, or even user level. Without them, the modern centralized generation electrical grid simply could not exist. Their continued healthy operation is a must. Their failure can have financial cost, environmental cost, safety implications, and even political ramifications. We all see examples every year where a transformer failure gets reported in the global media, especially if it brings down part of a grid. So why monitor transformers? Well, very simply stated, any transformer which does not feature some type of continuous online monitoring as part of its standard protection scheme is at risk of an unexpected failure. While monitoring will not prevent a failure, it will forewarn of that failure. You should perhaps consider the direct and indirect costs of a transformer failure. High replacement and repair costs and potential damage to surrounding equipment or electrically connected equipment. These costs can be huge, many times greater than the installed cost of a monitoring system. And one can quickly see the justification for some investment in online monitoring, and especially so on mission-critical transformers or transformers where no redundancy exists. The aspect of safety is even more significant. There is an obligation on employers to put in place engineered solutions that minimize risk to operating personnel, health and safety. And online monitoring of transformers provides for this through providing live visibility of the transformer condition 24/7.
Okay, thanks, Donald. So now let's have a look at the relationship between monitoring and diagnostics, as these two sometimes can lead to confusion amongst many. Monitoring is performed on a continuous basis, referred to as online. It is intended to detect an abnormal condition, to raise a flag when a condition has changed or something is wrong. When something has gone wrong, this is where more specialized diagnostic techniques, typically offline tests, are required, such as performing laboratory DGA, power factor, or even partial discharge measurement. These are verifications that are carried out to identify the nature of the problem and to determine whether the problem is serious or not. Often, the outcome of the diagnostic is just not to be serious, so no further action is required and online monitoring can resume. However, if the diagnostic confirms that the condition is serious, then further tests and expert opinion are required to determine what further action should be taken. So now we'll take a look at the difference between offline versus online. When we look at offline, in nature, this is something that is done periodically. It's something not done continuously. Let's take DGA as an example, which is an offline laboratory test. If we were to rely only on DGA technique alone, then the question would have to be, how often should a DGA be performed to guarantee maximum transformer protection? The answer is not that simple. For maximum protection, what would make the most sense would be to do a DGA more often than the fastest evolving transformer failure mode. Offline test does not come without its disadvantages. For starters, offline tests do not come without cost. They do take up time and tie up workers. And depending on the type of tests that need to be carried out, transformer may require to be taken out of service. For example, if we look at bushing and offline bushing testing, generally are carried out every 3 to 5 years and sometimes longer. They are typically completed by a third-party company, and tests are done at lowered voltages and under very different temperature conditions due to the absence of load. Under these circumstances, any quickly progressing problem would be missed and could result in serious consequences. So moving on to online monitoring techniques have come a long way over the years. They now permit much closer management of large power transformers. They provide early warning and concise information of developing faults. Online monitoring systems can empower asset managers to confidently operate their transformers until repair or replacement is convenient. In some cases, catastrophic failures have been avoided by using online monitoring systems. Therefore, when sizing up an online monitoring system, the system should have the capability to detect a wide spectrum of faults and abnormal conditions. Today, technology has expanded where it is now feasible to monitor the condition and operation of critical transformers, including each of its major components, such as the bushings, the on-light tap changers, and the cooling systems in real time. In the past, these systems simply recorded the data and transmitted it to a central point of analysis. Now, PCs located either directly on the transformer and in the substation or at a central server where they receive real-time inputs from transformer and its components to not only record operational data, but to allow for complex calculations. These complex calculations provide the owner a very clear picture of the operating condition of the transformer, as well as enable the use of diagnostic routines to determine the health of transformer and its components. So the key question everyone asks is, why do I do online monitoring? The fact of the matter is that transformers have a finite life, which can be shortened through abuse, ignorance of operating conditions. Online monitoring can extend the life of your transformer by making sure that you understand the current situation. Prolong life with care driven by knowledge of operating conditions.
Okay, thanks, Al. So we will take a look now at the chemistry of online monitoring, and in particular, we're going to look at the oil and the paper insulation in the transformer, the analysis of that, and we'll focus a little bit on the dissolved gas analysis. So oil is in contact with every component of the transformer internally. Any thermal or electrical stress occurring in the tank will be detectable in the dissolved gas signature of the oil. So by accurately measuring the dissolved gas content and analyzing this information, it is possible to diagnose a fault. Of course, oil analysis has always been a feature of good transformer management. Historically, it was limited to breakdown voltage determination and moisture in oil measurement, perhaps. From the 1960s onwards, with the advent of fault diagnostics, dissolved gas analysis emerged as the most important component of any monitoring program. Initially, fault diagnostics was considered an art rather than a science because expert interpretation was often required to get real value out of the DGA result. As time progressed, however, standard diagnostics emerged and matured, and in the 80s and the 90s, laboratories started to provide diagnostic reports with their DGA results. Industry bodies and standards organizations began to develop their own interpretation schemes. That situation has developed further since then. Today, there are multiple intelligent software platforms capable of sophisticated analytics on dissolved gas analysis. One example is Perception, a platform from GE. Designed as a fleet management tool, Perception is capable of performing transformer risk analysis. It can be used together with a DGA monitor, collecting data to evaluate the condition of a transformer and rank that transformer within a fleet based on its risk of failure. So how is this possible? How can we be sure that dissolved gases in the oil are produced by fault and have not simply accumulated due to oil aging. And that is where the years of experience utilities have gained in tracking DGA comes in. Mapping DGA results to faults during transformer repairs or even during postmortems. So gases are produced due to normal aging, and this is well known. However, the type of gases and the rates at which they are produced can be directly related to the stress condition the equipment is suffering under. Gases are generated at a rate associated with the severity of the stress condition. But in addition, different gases are produced at different rates under a given category of stress. There are many examples of this, and they are seen embedded in various ratios-based diagnostic methods or gas levels quoted in the standards. One of the simplest ones, often used to explain this phenomenon, is that acetylene, one of the diagnostic gases, is only produced when the oil experiences temperatures above 700 degrees centigrade. Sometimes you'll see this as being quoted above 1,000 degrees centigrade, but suffice to say, very, very hot conditions within the oil, the sort of conditions that will only be found around an electrical arc. So the presence of acetylene in your oil indicates the presence or the occurrence of an electrical arc in the transformer. Another example of how gases are mapped to faults is that carbon monoxide will only be found in the oil if the paper is degrading. So the more rapidly carbon monoxide is increasing, the more damage the paper is undergoing. Hydrogen is another gas, and it's a little bit unique. It's produced under all fault conditions. This is why we see single or composite gas monitors focused on hydrogen detection in the dissolved gas analysis market. Hydran, a composite gas unit with sensitivity to hydrogen in oil, has been manufactured by GE since the mid-1970s. And in fact, it's a byword for online DGA today. Really, if you have a conversation about online dissolved gas analysis, that conversation is sure to feature Hydran within its context. So we have a little bit of actual chemistry now. A typical oil molecule can be illustrated as a straight chain of C's, carbon atoms, bonded to H's, hydrogen atoms. On average, this chain would be about 16 carbons long for transformer oil. In reality, it's a little more complex than what's illustrated here, often with branches coming off, but this is good to illustrate the point. So as we watch the animation, we see inputted energy from a transformer fault break the molecule, with the resultant released parts of the molecule reforming into various different gases. You will note that a lot of hydrogen is produced, and as I mentioned earlier, hydrogen is produced under all fault conditions. What about the paper? The coils and internal cables of a power transformer are wrapped in a highly refined paper to provide structural support and to act as an insulator. The backbone of this paper, as in fact with all paper, is the cellulose molecule. And cellulose is made up of chains of a repeating sugar molecule, namely glucose. So cellulose is a biological product. It's damaged by heat. Let's say it's cooked by heat. So what are the breakdown products of this process? Let's just watch the animation for a moment. So we see that HOH, which is H2O, water, is produced. Carbon monoxide, carbon dioxide, and furan. If it's a low temperature fault that's affecting the paper or low temperature aging, you will get mostly carbon dioxide and a little carbon monoxide. You will also get the furans and water shown. If the temperature of the paper overheating is high, then carbon monoxide will dominate over carbon dioxide generation, and the rate of gas generation will speed up. If you monitor the concentration of carbon monoxide and carbon dioxide, consider the ratio of one to the other, and monitor the rate of gas generation, you can have visibility of how quickly the paper is being aged and even how far that aging has progressed. So let's take a look now at the asset manager's perspective to monitoring and to risk. Asset managers are busy people with many different responsibilities. Principal among these, however, is to ensure the continued availability of the electrical equipment to the grid or to the network. Operating within the confines of often tight CapEx and even tighter OpEx budgets, how did they do this? How do they prioritize that spend to ensure that the assets stay online? So traditionally, it was through good planning and routine maintenance schedules, but budgets continue to get tighter, especially OpEx budgets. Asset managers and maintenance crews are being pressed to do more with less. The inevitable outcome of this process is that an increased risk that electrical equipment will go offline unexpectedly and an outage will occur. Customers are without power, and inevitably the media will report this. If you Google the phrase transformer outage or transformer failure and look at the number of responses, and I did this morning, there were 12,000 responses approximately for each. Power outages are big news, and for a utility or an industry, they're bad news, they're bad PR. For an asset manager, it can even be personal, as they can feel some element of responsibility. So, it's bad news when a transformer goes offline, yes? Depending on your perspective, the risk and consequences to an unexpected failure can be different. Think of an industrial asset manager. What does a transformer failure mean to them? It means business interruption and the potential for property damage as an industrial process designed to stop in a controlled fashion goes offline suddenly. And the risks to the industry? Possibly the greatest risk is that the industrial assets are typically operated without redundancy, and industrial processes can be offline for long durations when repairs or replacements of the assets are affected. Failure of a transmission asset has different implications. In this case, it's probably revenue loss from power not carried, possibly contractual or regulator penalties, and maintenance challenges for an often already stretched maintenance team. And the risk on the asset, well, individually it's the same, but transmission companies have large fleets that are all at the same risk. So the challenge to manage the risk is multiplied. Thus, risk is application dependent, and an industry or utilities attitude to risk, and thus their investment in reducing risk will be driven by the potential cost of failure, both tangible, which can be financial costs, or intangible, which can be, for example, reputational damage. Risk is a statistical value, but the consequences of risk are very, very real.
Thanks, Donald. That was really interesting, and the animation was superb. So we'll have a look now at some online monitoring systems. When it comes to choosing the correct monitoring system, it can be difficult. However, there are some key factors that one can consider and that can help in the process of selecting the appropriate online monitoring systems for the application. For starters, having a basic understanding of the transformer behavior is critical. Going through historical offline data, looking back at DGA results, bushing results, and so on, can give you a good perspective on what may need to be monitored over what you think should be monitored. Other factors to consider, of course, is the cost of the transformer, the criticality of the transformer, and one needs to look at the overall risk. What is the probability and the consequences should a transformer fail? One thing is for sure, everyone's need is different. From the very basic composite single gas hydrant technology to the more advanced multi-gas photoacoustic technology, today GE's monitoring diagnostic product portfolio offers a wide range of integrated online solutions to assist users to better monitor and manage transformers on their electrical grid. So let's take a look now at both technologies. We'll first start at the hydrogen technology. Fuel cells have been on the market for more than 100 years. They come in many varieties and have been proven to work in diverse applications. In 1975, GE took this fuel cell technology and adapted it to enable the detection of dissolved gases in electrical insulating oil. The end result was an online, robust, compact, and self-sufficient device that detected a change in incipient fault gases in a transformer. If we look at how the gases are detected, a fuel cell is made up of three adjacent segments: the anode, which is the negative side, the electrolyte, and the cathode, which is the positive side. Essentially, a hydrogen sensor is built of two main components: a membrane, which is in continuous contact with the insulating oil, and an electrochemical sensor, or the fuel cell. The gases present in the oil, predominantly hydrogen and CO, will diffuse through the membrane and reach the electrical chemical sensor, where the gases will chemically react with oxygen, which is coming from the ambient air outside the sensor. This will generate a small electrical current, which is proportional to the concentration of the gases in the oil. The electrical circuit will measure the current, compute, and display the gases in concentration in ppm.
Okay, so 2 slides back, Al mentioned the photoacoustic spectroscopy. The multi-gas DGA instruments from GE use a detection system based on the principle of infrared absorption. Named photoacoustic spectroscopy, often just abbreviated to PAS, this analytical technique has been used for several decades in instrumentation used for monitoring urban or industrial pollution levels, for example. GE optimized the technology for the dissolved gas analysis application in about 2003-2004, and it has become a market-leading technology in the last few years. PAS has some very significant advantages. So in general, infrared systems, and there are many types out there, have the ability to operate for long periods completely autonomous of any user interaction. And this is a key requirement of any online monitor. Because IR systems do not typically require any carrier gases or other consumables, they can have a long service interval, 7+ years, for example. Primarily, for this reason, IR techniques in general and PAS in particular have come to dominate the field of online and portable dissolved gas analysis over the last 5 years or so. It's true that PAS is relatively new for dissolved gas analysis, GE taking the first products to the market in 2004, but there are approximately 10,000 infrared-based instruments operational worldwide performing multi-gas DGA. Clearly, IR technology is emerging as the leader in this field. Its ability to accurately trend evolving gases, evaluate the possibility of an active fault being in progression, and warn the user is second to none. IR-based multi-gas online DGA has really changed the face of transformer monitoring over the last 10 years. So we've talked a lot about dissolved gas analysis in general, the chemistry behind it, online dissolved gas analysis, monitoring. Let's take a look at an example of how effective the deployment of online monitoring can be compared to the traditional approach. So here we see just a screenshot taken from the previously mentioned Perception software. And it shows that for the period of time, the gas levels were stable. There's historical data that goes back a long time and shows a long period of stability. Then the gases rise pretty dramatically. Not all gases, but you can see in particular that acetylene and hydrogen are rising. So the fault has developed significantly in a short period of time. So the transformer was taken off load for a number of days, and then it was put back on load, and the gases rose again dramatically. Catastrophic failure of the unit was imminent, and this transformer was taken offline. From start to finish, this whole process happened over the course of 8 days. Traditionally, offline dissolved gas analysis would be performed once a year, and the likelihood of catching this failure with offline analysis would be very, very small.
Thanks, Donald. That was a great example of showing the difference between offline and online monitoring. So now we're coming into the last segment of our presentation, and we'll have a quick look at transformer life management. When we look at the direct and indirect costs of a transformer failure, damage to surrounding equipment, and high replacement costs, these are many times greater than the installed cost of an online monitoring system. The benefit of online monitoring system is not to prevent a fault from occurring, but to prevent it from developing into a major failure and to be able to warn the operator before this is potentially going to happen. For that reason, the gain from reduction in major faults will be somewhat attenuated by an increase in minor faults or predictive maintenance actions. With a good plan in place, life extension of existing transformers is possible and will help companies address a specific unit or population of issues.
Okay, so I mentioned we would take a look later at the bathtub curve. So now let's look at the impact that monitoring can have on the shape of that curve. Capable of detecting a fault at an early stage, monitoring, and in particular online monitoring, can reduce the incidence of failure and the severity of failure by providing the asset manager with the ability to run an informed condition-based maintenance regime. Not only is unnecessary maintenance work avoided, but required maintenance work can be carried out in a more timely manner, thus avoiding unnecessary progression of any fault. This all combines to lead to a reduced rate of failure in early, mid, and late regions of the life cycle curve. The most dramatic effect seen, the end of life region, can be pushed out by up to a decade, while overall risk of failure can be reduced by up to 50% over the entire lifetime of the equipment.
So in conclusion, the question everyone wants answered at the end of the day is, what can online monitoring do for me? Online monitoring solutions will provide asset managers with opportunities to save. 1. Focus capital budgets effectively. The significant cost of unexpected failure and even tighter controls on capital expenditures means that it is critical for companies to have an optimized asset replacement program. Putting in place an online monitoring and diagnostics system can identify the aging assets most in need of replacement and prioritize for timely repairs. 2. Focus maintenance dollars for best return. With comprehensive monitoring options that supply real-time diagnostics on transformer condition, companies can focus on direct resources more efficiently where they are needed. And 3, focus on prevention to cure outages. Assets are living beyond expected design life as they are now being asked to do more as energy demand increases. Unexpected failures could become an issue, resulting in energy outages that can cost companies dearly. GE's combination of technologies, advanced analytics, 24/7 monitoring, and expert analysis means developing faults can be detected before they cause unexpected failures. Tracy, I hand the ball back to you.
Thank you, Alfonso and Donald. That was a great session. On behalf of GE, thank you for attending our webinar. For more information about GE's monitoring and diagnostic solutions, please visit our website at www.gedigitalenergy.com.